Securing a system that has both safety-critical and infotainment or internet access is difficult, and it's made more difficult if the various pieces of the system have to talk to each other. It's common in applications such as cars and airplanes to have a situation in which eventually everything needs to talk with everything else. In this picture, as an example, for an airplane, the flight controls may be at the bottom, and then there's a gateway between that and the real-time vehicle management, things like navigation and lighting. There's a gateway between that and infotainment. And there's another gateway where passenger electronics may be able to connect into the infotainment system. If you think about things simplistically, you would say, well, gee, there's no way in the world I want my passenger-carried electronics to be able to talk to my flight controls. And you're not trying to do that on purpose. But what you find out is the flight controls need to talk to the vehicle management for things like weather forecasts and mission planning. The vehicle management needs to talk to the infotainment, so the infotainment system can display plane altitude, expected time of arrival, things like that. And the passenger electronics have to talk to something. So while you are not directly trying to connect the electronics to the safety-critical flight controls, eventually you can get there with multiple hops because everything has to be talking to its neighbor. Mitigating this kind of risk requires a lot of attention to detail and many different types of mechanisms. For example, you can insert a firewall, so when we have a gateway, you'd want to put a firewall in there to restrict the type of traffic that can get through. You probably also want to add integrity checks in data fields and use some sort of cryptographic to support to make sure that the passenger electronics cannot forge a message that goes directly to the flight controls. You can encrypt. It's probably better to use digital signatures and other authentication mechanisms, but the catch is that ultimately everything's connected to everything, so you have to pay a lot of attention to security. Making things worse, legacy embedded networks are completely insecure. There's no encryption, there's no authentication, and all the integrity checks are non-secure checks such as CRCs on a good day or checksums and parity on a bad day. Retrofitting existing equipment and improving embedded networks that are widely used in industry is a long-term challenge that remains generally open. Getting secure communications inside the bounds of an embedded system is a very tricky area. Ideally, what you'd say is, well, I'll put an air gap in, meaning that there's no actual wire connecting the system to anything else. But that's just infeasible because there's huge demand for internet-connected devices and general improved functionality. So while that was the story that used to be told, that's just unrealistic these days. A lot of the approaches involve putting in a firewall and rejecting risky packets. But over time, we're going to see pressure to actually change the communication protocols inside embedded systems to be more secure. This area has a lot further to go, and you'll be seeing continued research and continued pressure to improve the security inside embedded systems over many coming years.